This video was made possible by StruSoft. One of the greatest strengths of computational design is the power to create multiple variations in little to no time. I will now demonstrate this with an example of a structure with slab and wall elements. Here I have a simple model in Rhino. I can freely edit this by selecting the objects and moving them around. Let's imagine that I want to add another wall under the slab, and I want to optimize it to minimize deflections. I can either perform an iterative analysis, or I can create a load of variations of this model and then choose the one that has the best performance. The first one we can perform with Grasshopper by using iterative solvers like Galapagos or Wallace, but we will first try the second option. The upside of that is that you can visually see all the variations next to each other. We will cover the Galapagos optimization in this video series, so make sure to like this video and subscribe to the channel. Let's first cover the plate and wall components which are a part of FEM-design Grasshopper kit. They currently have identical inputs and outputs. Let's start with the plate. First, input the surfaces. We have defined one by using a rectangle here in Rhino. Then you need a thickness. I have inputted this in meters. Next up, we have the material. We have covered how to select materials previously in this series. Then for the slab, we have connected the orthorhomorphy, the edge connections, and the local coordinate system. The surface, thickness, and material are necessary inputs, and the rest are optional. Now for the wall, we have added some eccentricity, and we have given it an unique identifier. All of the elements are then merged and connected to the structural elements input. Next, we define the model. The slab has been defined in the plate layer as a rectangle. The walls have been defined also as rectangles, but on the wall layer. I then use query model objects and create boundary surfaces from the rectangles. I use the series component to create a list of vectors which I use then to move the surfaces. If I increase the count, I will start getting more variants of the wall-slab combinations. Because the slab is symmetrical, I have decided that the last variation has the wall in the middle, and the other variations have the wall moved by an equal step between the variations. I can see the length of the slab here, and I can see the length to the wall here. If I edit the slab length, this will automatically update all of the variations. Next, I will run FEM-design, and we can get to analysis and look at the deflections. I will turn on automatic numeric values by objects and increase the precision. With no surprise to anyone, the deflections are the smallest when the span is the smallest, and this happens when the wall support is placed in the middle of the slab. This, however, was just an example on how you can utilize the power of automation when analyzing different scenarios. The outcome might not always be as obvious as in this case.